So hello, everyone. My name is Jacob. I'm a professor in Bear working on trustworthy machine learning. And today I'm going to talk to you about using AI to understand AI. So what's the motivation here? So the basic motivation is, right, there's this kind of rapid proliferation of AI systems being deployed. Right, we had GPT-4, then we had Mistral, then we had Sora, and then we had Claude 3, right? And they keep getting better, but they also keep getting more complex, and they are doing more and more different things, right? And often they do unexpected new things, right? We get kind of emergent behavior where suddenly there's new behaviors or new capabilities that might either be, intrinsically create safety problems. For instance, when Microsoft deployed Sydney, it would sometimes threaten users to try to get them to behave the way it wanted them to, which obviously we don't want. Or extrinsic problems, like someone uses this to do like a phishing attack or design like chemical weapons or something like that, right? So we want to kind of understand the surface of behaviors so that we can actually responsibly use and control and deploy systems. But how can we kind of keep pace with all of the new problems that we're seeing every day? And so kind of the key idea and the key motivation of this talk, I guess the starting point was, well, can we use large language models to understand large language models, right? So LLMs are good at a lot of things. They can process a lot of data because they have large context windows, and they can explain things to us. So maybe they could just kind of look at the behaviors of either themselves or some other LLM and help us understand what's going on. And now this is kind of good because now as models get better, understanding does as well, right? So now instead of new LLMs come out, we have new challenges. Also new LLMs come out, we have new solutions. And I guess since the first time I gave this talk, we went from the LLM world to the VLM world. So I'm going to talk not just about LLMs, but generally using AI systems to understand AI systems. So how can we do this? Well, first we have to figure out what we mean by understanding. And so my claim is that many forms of understanding basically reduce to statistics or data science problem. So what do I mean by this? Well, one thing we might want to do is, given data about a model's behavior, identify patterns in the behavior that we might care about. Like, on this subset of inputs, coding models are more likely to have security vulnerabilities. Another thing we might care about is to explain the important sources of variation in the training set, right? Like, what is, what is actually going on in the training data? Maybe there's certain biases in the training data that we care about and might want to correct. Another thing is maybe we want to actually do some form of like active learning, right? Actively generate inputs that elicit some problematic behavior, or at least that we're going to try to elicit the problematic behavior to see if it's there so that we can fix it. And so all of these are basically a statistics problem, right? This is like kind of like PCA. This is basically, also some form of like feature learning or clustering. And this is basically active learning. And so if we can get LLMs to be good at, in some abstract sense, doing statistics, we can tackle these problems. So I'll give a concrete example of this in a second, but kind of staying at the conceptual level for now, what does it mean to do statistics? Well, I claim that it is basically this four-step pipeline, or most statistics looks like this four-step pipeline. We look at some initial data. We form some hypothesis. Right, so this might be like we look at a bunch of instances of behaviors of some model that we're trying to understand. We form some hypothesis about how it tends to behave in general. Then we need to formalize that as some like actual quantitative hypothesis. Like say it's 50% more likely to output code with a security vulnerability if the input has grammar errors. Maybe that's like a hypothesis, right? Of course, that's still a kind of qualitative hypothesis because it's not yet a kind of like formally defined hypothesis. So we need to formalize it somehow. Then we test it on new data, right? That could either be held out data from the same distribution, or we could try to get at some notion of causality with out of distribution or actively collected data. So, so this is the statistics pipeline, and so I'm going to give you a few case studies where we kind of have a problem, we reduce it to this kind of form. We automate each step with either LLMs or VLMs, and then we use this to better understand models and find problems with them and sometimes even fix them. The key difference here is that we're using LLMs. So in traditional statistics, this hypothesis might just be some mathematical function. Like we're saying, average treatment effect is greater than 0 or something. But here, H is going to be a natural language string. And so actually a lot of the problem is going to be about how to formalize what a hypothesis that is only stated in natural language means in a way that we can quantitatively test it. Okay, so that's the high level. The very concrete first case study I want to talk about is finding failures in CLIP. So who here knows what CLIP is? Okay, so maybe 3/4 of you. So CLIP is an embedding model that embeds images and text jointly. So CLIP is an embedding model that embeds images and text jointly. And if you haven't heard of it, you've probably heard of things that use it. So it's kind of the backbone of Stable Diffusion, Midjourney, DALL-E. Basically, all of these text-to-image models use CLIP as their first step. And these models can do pretty amazing things. Here's a prompt in empty glass. It shows you this. A family of 5 members. It shows you this. A man descending a mountain. It shows you this. There's no star in the night sky. It shows you this. So you get these amazing pictures. The problem, though, is that all of these pictures are wrong, right? So I said an empty glass, but this is actually a full glass. I said a family of 5 members. This is actually a family of 6 members. This is a man ascending a mountain, not descending a mountain, and there are many stars in this night sky. So you get these amazing results, but you kind of still have these very basic failures. And the plot twist, actually, in this case, is that all of the failures I showed you here were found automatically by a large language model. So I didn't come up with these myself. I just ran some code that my students, Eric Jones and Peter Tong, wrote and handed it the model, and it kind of chugs along for a while, and then it outputs this and many other things. So I'm going to tell you how can we actually design a system that's going to automatically find all of these failures for us. So there's kind of a few key ideas. So you remember that CLIP is an encoder model, so it kind of embeds inputs. So the first thing we're going to do is we're going to find what I'm going to call hash collisions in this encoder, basically pairs of inputs that kind of collide in the embedding space. And this is kind of a good source of potential errors. So this kind of gives us a way of efficiently finding a lot of errors. This gives us kind of individual errors with the model. We're going to then use GPT-4 to categorize these errors into kind of coherent generalizable patterns, and then use these patterns to generate new example failures. And in fact, you can even generate them in new domains that are totally different from this kind of initial set of hash collisions that you found. So we'll actually see, for instance, that you just take collisions from kind of regular images, and then you can transfer it to, say, the self-driving car domain. So these are kind of the key ideas, and we'll actually see in a second that they actually kind of correspond to these 4 steps of the statistics pipeline. So, the first step of this pipeline, I said, is you look at some data, right? The 4 steps, remember, look at a data, form a hypothesis, generate a hypothesis, formalize a hypothesis, and test it. So the first thing we need to do is look at data. So, so what's the initial data going to be? Well, before I can say that, I need to give you a little bit of background about CLIP. So CLIP can take as input either an image I or text T. And either way, it's going to produce a vector. Depending on the architecture, either say a 768 dimensional vector. The dimension depends a bit on the particular model, but it's going to output some vector. And what is it trained to do? Well, it's trained on a bunch of images and their captions. And it's trained to generate embeddings such that each image has high cosine similarity to its caption and low cosine similarity to all of the other captions. So it's kind of a contrastive loss. Right, so in particular, it's trained such that if T is a text description of an image I, they should have similar embeddings. Right, they should have high cosine similarity. So the idea now is if I can find two text strings, T and T prime, that have very similar embeddings under clip, but that describe different visual concepts, then at least one of them has to be wrong, right? Because that's going to kind of mess up this matrix. So basically, we're going to search for pairs T and T prime that are collisions in this sense, that they have similar embedding, even though they semantically mean different things. So concretely, we're just going to collect some corpus of text inputs. Let's call it T1 through Tn. And then we're going to embed them under clip. And then we're also going to embed them under another model called Distill Roberta, which is just a text-only model. We're going to use that for checking checking that things are actually semantically different. So basically, we're going to find pairs Ti, Tj that have high clip similarity, but low Roberta similarity. Right? So this is saying clip thinks they're the same, but actually they're not the same. So some examples that you get out of this would be like two girls walking down the street and two women walking down the street, or a tall glass on the table versus a short glass on the table. Clip thinks those are the same, but Roberta thinks they're different. And one thing that's nice here, right, if we're looking for hash collisions, is we get to exploit the birthday paradox. Right, so there's like for n data points, there's n squared potential hash collisions. So this gives you a kind of very efficient way of finding problems with the model that's, in some sense, quadratically faster than if you just do it naively. Well, now we just use LLMs. So we basically take all these individual failures, which are just text inputs, and we feed them into GPT-4. And we give it this prompt. So this is kind of the magic prompt, although, I mean, the specific details matter a bit, but not like fully. So basically we say, okay, I'll provide a series of data for you to remember. Subsequently, I will ask you some questions to test your performance. Here are some pairs of prompts for you to memorize. Then we give it, K of the failures that we found, where you just pick K to be whatever can fit in the context window of GPT-4. And then you give it some instructions. You say, I'm trying to find failures with an embedding model. The above are some pairs of sentences that encodes very similarly, even though they're conveying different concepts. Using these specific examples, are there any general types of failures you notice the embedding is making, or any common features that the embedding fails to encode? And then you kind of give it some more descriptions. So you give it this, and then what do you get out? Well, you get a nice list like this. So conveniently, it actually uses a consistent markdown list format, so it can actually programmatically parse out the different hypotheses it gives. So note, what is this trying to do? This is trying to go from these individual failures to kind of consistent patterns, right? So it's saying, okay, what are the consistent patterns it found? Well, one is saying, okay, negation. Embedding models may not correctly capture the negative context in a sentence, leading to similarities between sentences with and without negation. This can result in incorrect visual representations, as the presence or absence of an action is significant in image or video generation. And then there's other ones like temporal differences, quantifiers, and so on. A nice thing here is that you get not just this category name, but an actual description. And this description is sometimes helpful, right? This is saying we don't just care about generic negation, but actually perhaps the presence or absence of an action in particular could be relevant. So this elaboration sometimes has useful information. Okay, so now we have these hypotheses. So that was step 2, right? Generate a hypothesis. How could I formalize this hypothesis? How could I tell if this negation hypothesis is actually true? Or how could I quantitatively measure the extent to which this negation hypothesis is true? So this is an exercise for the class. Any thoughts on how I could actually, quantitatively check or test this negation hypothesis? So what I could do is I could basically try to generate a bunch of new examples based on the hypothesis, and then see if those new examples actually are give you these hash collisions consistently. And I might even want to go further and test that they don't just give hash collisions, but actually lead to failures downstream. the kind of key takeaway here is that we'll say that H is a good hypothesis if it can be used to generate new failures. This is also nice because it kind of actually like grounds it in usability. So to do this, we basically prompt a LLM to generate new failures using the hypothesis H as a context. So basically we say, write down 41 additional pairs of prompts that an embedding model might encode similarly, even though they would correspond to different images used as captions. Use the following format. So we kind of like force it to use a specific format so that we can again programmatically parse its output. And then we say, okay, you'll be evaluated on how well you perform. Your sentence structure and length can be creative. Extrapolate based on the failure mode you've summarized. Be both creative and cautious. I actually don't know if that last part matters, but Eric added it. So and he's pretty good at these things. So, but we did not do a careful ablation. Like it may or may not matter. And then you just provide the description of the failure mode, like the negation thing from the previous slide. So then we do this, and then why did I pick 41? Well, that's just the number that GPT-4 is willing to generate. You can just keep asking it for an additional 41 if you want more. So then you get a bunch of these, and so we're going to check if these prompt pairs actually do have very similar embeddings while having different Distill-Roberta embeddings. And then we'll check if when you actually feed them into something like Stable Diffusion, it creates problems. So this is testing the hypothesis, right? So first of all, let's just look at the hash collisions. So this chart's a little bit complicated, so let me explain to you what's going on. So there's different models that we used to generate the hypotheses. Right, so the list I showed you came from GPT-4, but we also asked Claude and GPT 3.5 to generate their own list of these high-level hypotheses about the systematic failures of the model. And the thing is that different models provide different hypotheses, right? So there's actually two things we care about. There's like, did the model have this hypothesis at all? And then if it did, what was the success rate at generating new failures? So as an example, right, this is saying that like GPT-4 and Claude both generate temporal differences as a hypothesis, but GPT 3.5 does not. Okay, so that's what this down here is saying. This is just the different failures. And then COCO and SNLI are two different data sets of image descriptions that we use to do the initial scraping of hash collisions. So this is trying to get a sense of how much does the initial corpus affect what hypotheses you get out. And in fact, it seems to affect it somewhat. Like SNLI seems to get this like action state differences, whereas COCO does not. I think COCO generally has kind of like more static scenes than SNLI, so this kind of makes sense. So this is saying that the underlying data matters. Different models come with different things, but in general, if a model comes up with a hypothesis, it tends to have a pretty good success rate. Like most of these things are kind of around 80%. Some are more around like 30 to 50%. But they are all pretty good at generating these hash collisions. Interestingly, actually, sometimes even for the same thing, more powerful models do better. So for quantifiers, GPT-4 does better than Claude. Why is that? Well, it's just because of that elaboration text after the quantifier hypothesis. Like GPT-4 gives kind of a richer elaboration that's more useful for generating new failures. Okay, so this is hash collisions. But what we also care about is, can we generate actual failures in downstream systems? So we did this. We kind of created a UI to test this. We took, basically what did we do? We took these pairs of prompts that were supposed to be collisions. Then we randomly fed one of the two into, say, Stable Diffusion or some other text-to-image model. And we look at the image that was generated. And then we asked a human, I guess in this case, just one of the authors of the paper, but who didn't know which model or system this came from, does this image correspond to prompt 1 or prompt 2 or neither of them? Or are these prompts actually not different? Like they don't actually describe different images. So what would count as a failure? A failure would be if the image came from prompt 1, but the labeler said prompt 2, or if the labeler said neither. If it came from prompt 2 and the labeler says prompt 1 or neither, then that would also count as a failure. So we're trying to understand what's the rate of failures. And we find, I guess, first of all, it is pretty high. Secondly, it actually depends on what similarity threshold we use. So basically, once the clip similarity, like the cosine similarity of the clip embeddings, so basically, right, like what's the threshold you want to use to count something as a hash collision? If we pick as our threshold something around 0.9, then the rate at which this leads to like actual failures in downstream systems is about 80%. And just to show that this is like, meaningful, we had a baseline system that basically was the same as the system I just described, but instead of GPT-4 being given a bunch of data to help it generate hypotheses, it was asked to just kind of brainstorm hypotheses in kind of like not grounded to like the actual failures, and then comes up with a different set of hypotheses, and those hypotheses only give you like a 20% failure rate. So there really is like a significant effect from having these kind of data-driven categories. And then the final thing is you can just generate failures in new domains, right? So if you say, actually, I wanted you to generate failures that are about self-driving cars, but using kind of like these high-level categories you had come up with, what would you generate? GPT-4 can do this just fine, and you get things like the car is on the right side of the lane when it's actually on the left side. This is not a green light, but it's actually a green light. Or like red light, where this is like a green light. So you can kind of transfer it to new domains, which is kind of an additional proof of external validity. Okay, so to summarize, right, we kind of did all these 4 steps of the statistics pipeline, right? We had this, to get initial data, we scraped hash collisions from a text data set. To generate hypotheses, we prompted GPT-4. We formalized the hypothesis by looking at the success rate for generating new failures. And then for new data, we actively generated new examples in this new self-driving domain. And one thing that I think is interesting here is like, in some sense, a lot of this was just like prompting and embedding, but not in a kind of naive way. We're kind of having all these models like work together kind of in harmony to do this kind of cool thing that you couldn't necessarily get from just a single prompt. Okay, so any questions about this? This is kind of the first case study I wanted to tell you about. Yes?
Did you see any differences in failures that didn't have high clip similarity? Like maybe a different mechanism was causing a failure?
Oh, you're saying like the stuff around here, like why?
Yeah, exactly.
It's a good question. I actually don't know. I didn't look into it, but I think it's something that, yeah, I'm curious about it. So yeah, thanks for asking that.
Sure. One more thing. When you were having the models generate prompts, generate hypotheses, did you do a lot of playing with prompts that and try, N-shot and other techniques like that?
We spent a while playing around with prompts. I don't know if we tried like in-context learning specifically, but yeah, I think we spent like a decent amount of time on kind of like engineering the prompt to be good. Like I said, I think it's not extremely sensitive to like the exact prompt we used, but I do think, I would guess that like 50% to 75% of the specifics matter, and the other 25% just like happen to be there because we didn't like carefully check exactly what was needed. Yeah. Any other questions? Yes?
For the failure modes that you had on your graph, was that like a superset of all the failure modes identified by all the models across the different data sets?
These? Yeah, so this is an exhaustive list. So, I think what you'd really like is like an even longer list of kind of everything. This is still pretty good in that, like, for some of these, there was like an entire paper written just about that one failure mode. So, we've gone from getting one failure mode per paper to getting 14. But yeah, ideally we would be getting like hundreds or thousands of just like understanding everything in the model. And I think we're not there yet, but I think that's where I'd like to be. Right, you can kind of see like, maybe Coco's like very slightly better, but I think, yeah, it kind of seems to me like mostly you just want a lot of diversity. And Coco and SNLI had like different types of diversity, so they were kind of both good in their own way.
Is it possible that there is some kind of leakage happening here? I mean, so basically GPT-4 has a knowledge cut of about 23, and the time code was released will be way, before that. And is it possible that GPT-4 has some knowledge about?
Oh, like it's like read the papers that describe the failures?
And compared to GPT 3.5, it probably have an earlier knowledge cutoff, and so therefore it's weaker on this because it does not have the knowledge about those errors.
Yeah, it's an interesting question. I don't think I have a way of ruling that out. I would guess this is not like a major factor, partly because like many of these are like we're not in the literature. Although, okay, I guess there could be a more subtle thing, which is just like people talking in general about the problems that models could have, and then this like gives you a source of hypotheses. So I think that that seems really plausible to me. I think so the main piece of evidence I have against this being like the primary thing that's going on is that if you're just kind of brainstorming if you just have GPT-4 brainstorm from its prior, then it's only getting this like 20% success rate instead of 80%. So somehow like the actual specific data does seem to matter. Okay, so let me talk about another kind of case study. So this is statistical modeling with natural language parameters. This is a kind of research direction spearheaded by my student, Reichi Zhang. So I guess first let me just talk about a kind of abstract task that I think is interesting, and then I'll explain to you why we want to solve this task. So the task is, given two text data sets, D1 and D2, we want to find the difference between them. But the difference should be specified by a natural language string H. So this is basically binary classification, but where the classifier has to be stated in natural language rather than as like some neural net. Right. And so why would you want this? Well, I mean, if you just care about classification accuracy, then you probably should use a neural net to do your classification. But the problem is then the neural net's kind of a black box. We don't understand what's going on. If we have a natural language string, now we actually like understand what the actual difference is. So here's an example. So suppose this was D1 and this was D2. So can someone give me a natural language string H that will distinguish D1 from D2? Well, I'm looking, like H should be like a rule that like tells you what D1 or D2 is.
Oh, I see.
Yeah.
What language is this written in?
Yeah. So basically it would be D1 contains more French sentences compared to D2. Or like D1 is French and D2 is English, right? Okay, so this one is, right, so this one's pretty easy. Like we can all once we understand what the task is, we can all get it pretty quickly. I had a hard one, but that one took people too long to figure out, so then I skipped it. But I guess maybe I'll say in general, the actual examples can be a lot harder and more subtle, right? Like we might be looking for patterns where there's like maybe like a 10% difference between one data set or another, or the like examples could be like much longer than just these simple sentences. So what are some example use cases of this where we would want to separate two distributions? So one is I might care about distribution shift, right? So I trained on one distribution, I'm testing on a new distribution, I might care what are the differences, right? So maybe I find out that the test distribution involves more formal writing than the training distribution. And so then that's a potential source of OOD failures. Or I could look for spurious cues in a data set. So say I have a spam classification data set, but I find out that the positive class contains more URLs than the negative class. Well, that means URLs might be a spurious cue for any classifier that I train on this data set, where like I really want it to be detecting spam, but instead it detects the presence of URLs. I can also use this to do automated error analysis, right? Maybe I find out that GPT-3's mistakes contain more positive or uplifting language than TK11 billion's mistakes. And this like maybe teaches me something about the errors of these two models. I could also use this maybe for kind of social science applications, right? So maybe I look at a bunch of tweets and I determine that public opinion from this year is more optimistic about the pandemic than last year, right? So these are all like pretty natural use cases that you would care about that basically just come down to this like explainable classification problem. So we're going to do this using LLMs. Basically, same 4-step pipeline. Look at the data. Well, fortunately, the data is just handed to us here. We just have D1 and D2. So then we need to propose a hypothesis. Well, how do we do that? We can just prompt it. So we can say, OK, here's a bunch of A's, which are all from D1. Here's a bunch of B's, which are all from D2. Compared to group B, each sentence from group A has what property? And then I guess this is what GPT-3 does. When we did this paper, it was with GPT-3. You can now do GPT-4, which will work even better. But it generates a bunch of hypotheses. So like it says, OK, is more positive, contains the word chapter. OK, that's technically true. These both contain the word chapter, is longer, also technically true. But some of these hypotheses are actually generalizable, some are not. Why wouldn't they be generalizable? Well, the context window of these models is limited, so you can only put so many examples into the context window. And so you might have this problem of like, there's something that's true on like the 30 examples you looked at, but it was just kind of a spurious, or not spurious, but like a statistical artifact. So we'd ideally like to test these hypotheses on many more examples. So how could we do this? Any thoughts? Like how could we figure out which of these hypotheses like are really like actually generalized to the full data set? So the nice thing is basically once you have the hypothesis, this context window problem goes away, because if I want to just test the hypothesis, I can do a for loop and test each example in my data set individually. So I no longer have the context length problem. So right, we kind of start with these two steps that we've already done, looking at the data and forming a hypothesis. And we'll say, to formalize this hypothesis quantitatively and see if it's true and test it on new data, we're going to say a hypothesis is good if it helps us tell D1 and D2 apart. So what do I mean by this? OK, intuitively, if I gave someone an example that was randomly chosen from D1 or D2 and they didn't know which, but then I tell them H, I tell them the hypothesis, they can consistently classify D1 versus D2. Now, humans are expensive, so we're going to use LLMs instead. So in a bit more detail, so here's just some formalism. If this is confusing, don't worry about it, because it's just saying formally what I just said intuitively. But there are some kind of important formal details. So basically, as an example, suppose that we had the hypothesis H, which involves more formal writing. Well, we can interpret this as basically a 2-argument predicate that takes in 2 sentences and outputs binary truth value 0 or 1. How do we interpret it as a 2-argument predicate? So we say h of x1, x2 for sentences x1 and x2 is just the truth value of the sentence x1 involves more formal writing than the sentence x2. And so that kind of, in principle, has some well-defined truth value. Humans could evaluate it, but instead we'll just ask an LLM to evaluate it. So we'll say, we'll define h of x1, x2 to just be like what an LLM would say about the truth value of the sentence. And we'll say h is a correct hypothesis about how D1 and D2 are different if in expectation over a random sample x1 from D1 and x2 from D2, h of x1, x2 is, did I flip this? No, I think this is, right. You want it to be basically as close to 0 as possible. This is saying that it's always bigger on x1 than on x2. Wait, no, did I get this wrong? Sorry, I think you want it to be as close to 1 as possible. Yeah, much bigger than. Okay, last time I had it that way, and then the audience convinced me it should go this way. But, okay, the point is you either want this to be very close to 0 or very close to 1. There's some sign thing. But the thing you definitely don't want is for it to be close to 0.5, because close to 0.5 would mean that, like, it can't distinguish x1 from x2, right? It's, like, basically equally likely to say yes or no. You want it to, like, always say the x2s are bigger than the x1s, or the x1s are bigger than the x2s, but not, like, I have no idea. Okay, so how do we implement this? Like I said, we'll do it by querying an LLM. If you compare like mturk costs to GPU 3.5 turbo costs, it's about a 1,000x reduction in cost, which is significant. Okay, so here's the overall system, right? We have this hypothesis proposer that takes in data, generates candidate hypotheses. Then given these hypotheses, we have this hypothesis verifier that basically evaluates and re-ranks these to say which ones are the best. A really nice thing is actually, you can also steer the proposer based on the use case, right? Because this proposer is a language model. So I could say, I don't just want hypotheses that are true about this data, but that are true and relevant to some use case I care about, right? Maybe like I only care about style, but not about like length. Or I care about topic, but not style. Or like, I don't know, maybe I have like 2 corpora that are in different languages, but I don't care about that difference. And like by default, that's the first thing it's going to propose. So I have to tell it, no, I really don't care about language. Tell me about the other things, right? So you get this really nice like steerability or controllability because you're working with LLMs. Okay, so just to go over a few use cases of this. So the first one is you can find spurious cues in data sets. There's this data set on subjectivity analysis, so basically determining if a statement is subjective or objective. And if you ask it what's the difference between the subjective and objective class, it says, is a quote from a film review. Actually, when we first saw this, we thought we had some like bug in our system. But then we read the paper that proposed this data set. And apparently the 2 classes were like IMDb and Rotten Tomatoes. Because the idea is like IMDb is objective and Rotten Tomatoes is subjective. So actually the difference was that it was a quote from a film review for the subjective class. There's this data set called MNLI, which is a natural language inference task. So it asks whether like one sentence entails another sentence or not. And there's this well-known spurious cue, which is that having a negative verb like not is highly correlated with non-entailment. And so people, this is like well known in the literature, but our system recovers it. And then this spam classification thing, in fact, is actually true. So the spam class has a high number of hyperlinks, and if you take, if you train like BERT on this data set, or like you fine-tune BERT on this data set and use it as a spam classifier, if you take your own emails and add hyperlinks to them, it does start to classify them as spam. So it's like a real spurious cue. Also, automated error analysis, we kind of already talked about this, that GPT-3 query makes errors more often on language that is positive or uplifting. And there's actually a lot of other applications. So if you're interested, we actually created a data set with 675 different use cases across different domains. Our system currently only gets a subset of these cases. But if you're interested in kind of like automated explainability and kind of like automating science, kind of like social science with LLMs, this is a really cool data set that I'd encourage you to check out. Okay, All right, so in summary, we did this kind of same 4-step process. We had this initial data where we had these two text distributions. We generated a hypothesis by prompting GPT-3, formalized the hypothesis as the success rate on distinguishing samples, and then here the new data was just held out samples to test that the hypothesis was in fact true. So we can extend this beyond binary classification. So the kind of general insight is that, given any natural language predicate H, we can basically, it basically induces a feature function. Like my claim is that a natural language string is actually like a feature. Right, so what I mean by that is we could define as denotation, which is a function from strings to 0, 1, which is just the truth value of this predicate on that string, right? And so we're not stuck with just having one feature, right? Like most models have lots of features, right? So for instance, we could define an exponential family model where p of x given, vector w and a list of predicates h is proportional to e to the w1 times h1 of x and so on up through wk times hk of x, right? So this is basically a one-layer neural network, right? Kind of like a one-layer MLP or something, but where the first layer, instead of being this matrix, is actually this list of strings that define these feature functions, right? So this is kind of equivalent to a one-layer neural network, but where all the features are explainable instead of being kind of arbitrary vectors. And more generally, you can use this as the basis of lots of more complex models, like topic modeling, low-rank factorization, clustering, and so on. So here's just one kind of cool example use case. So say that you say, okay, I have this data set of images. I'm classifying dogs versus elephants, and I want to understand how their backgrounds are different. And so then it will say, okay, I'm going to try to find clusters where the proportion of dogs versus elephants is very different in each cluster. So it kind of comes up with these three, where the three backgrounds are jungle, white background, and sand, where elephants are much more likely to appear in the jungle. Dogs are much more likely to have a white background, and then they're actually about equally likely to appear in sand. So this is kind of just a fun application, but the point is, how did I do this? Well, basically, I wrote down a contrastive clustering loss function, and then fit a model to it. But I had terms in the model that were just these natural language strings. So how does it work? It kind of works as a kind of alternating maximization problem, where you alternate between maximizing the continuous parameters in your model and then using GPT-4 to make proposals for the discrete parameters, these like natural language strings, and you kind of like go back and forth. So it's kind of like the EM algorithm or other kind of alternating maximization algorithms, if you've seen that. I think this might actually be on archive now. We submitted it to a conference like a few months ago, so you might actually be able to read about this. But yeah, I think this is really cool. It kind of opens up like a whole kind of like new library of statistical models that you could write down. Another thing you can do is, instead of just trying to explain behaviors of models, we can try to understand their representations. So this is another project I did with actually with Yossi Gondelsman, who is a student of Alyosha Efros. And Yossi and Alyosha and I kind of collaborated on this. So what we did is we went back to CLIP, that text image model, and we said, okay, we want to understand what like the different parts of CLIP are doing. So most of what CLIP is these things called attention heads. So we said, okay, what are all of the attention heads doing? And so for each attention head, we actually tried to find a basis for that head. So a set of directions that kind of explain the variation in the behavior of that head. But with the constraint that each direction actually corresponds to some text string, so that all of the directions are explainable. So think of this as like explainable PCA, like PCA with the constraint that every component is text-backed. So if you do this, you get some cool things. So, for instance, like one of the principal components for layer 22 head 8 is a photo with the letter V, and you kind of see, yep, there's a V, there's a V, there's a V, there's a V. There's like image with polka dot patterns. You kind of get that. And what's really cool is that the heads actually seem to specialize in their behavior. So this like layer 22 head 8, if you look at its like top 10 principal components, it's like a photo with the letter V, a photo with the letter X, a photo with the letter like Y, a photo with the letter W, a photo with the letter A. It's basically seems like, one of the things this head does is it just like pays attention to letters. There's another one that's like paying attention to locations, another one that's paying attention to numbers. And so what are some cool things you can do here? One is you can use this to actually find adversarial examples. So for instance, the head that pays attention to numbers, it actually pays attention to two types of number. So it has components that are like an image with two objects, and also an image with the number 2. So it's actually, there's like a single component of clip that is both counting things and like doing digit recognition. So then if you give it an image that has both digits and like some quantity of objects, and you ask it like how many objects there are, it'll actually answer, instead of the number of objects, like the digit that you drew. Like it basically stores both of these concepts in the same place, so it gets confused between them, and you can use this to generate adversarial examples. Another thing you can do is you can remove spurious cues. So there's some tasks like classifying different types of birds where there's a spurious cue of like the background that you might not want to pay attention to. And so you can just find the attention heads that are like paying attention to background and ablate them from the model. And this significantly increases out of distribution accuracy on kind of these spurious cues. So you can also use this to repair models. Okay, so here's just like some more examples of this. So this is what I was talking about with like the number head, like image with 6 subjects and image of the number 4, shape head, color head. In addition to this, you can actually also ask, what do these heads care about in the image? So for instance, this layer 22 head 1 is a shape head, and I guess first of all, what it cares about is this thing, right? And if you say like, and like the thing it like most like kind of thinks about this is that it's an isosceles triangle, right? And there's this other one, the color head. The thing it most thinks about this is like image with an orange color. And also if you kind of like put in different descriptions and ask like what's important for that description, it will also kind of like attend to the right things, like photo of hero versus photo of a camel. So there's lots of cool stuff in here. I would recommend checking it out. The final thing I'll just say is there's a paper that didn't make it into here, but I just want to give like a very brief shout out to it since I have time. Is we have this, oops, wrong thing. We have this recent thing that extends the describing differences stuff to images. So given like some data set of images, I can tell you what's different between like the top and bottom row. In this case, it was people posing for a picture. So like all the stuff up here has people posing and all the stuff on the bottom doesn't. And so you can use this, for instance, to like automatically like do error analysis for image classifiers and say find the different, like you have 2 image classifiers, when does one perform better than the other? And you can kind of do the whole gamut, but with images instead of text. Okay, so I will stop there and take any questions that people have.
This might be a dumb question, but what's involved in taking out the basis of an attention head? Because that's a pretty nonlinear map, right?
So basically, on any given input image, the attention head has some activation vector. So now if I have n input images, I get like an n by d matrix, right? Because if d is the dimensionality of the embedding. And so I can ask, what are the principal components of variation in that n by d matrix? And I basically want like a basis that explains those components as well as possible.
Gotcha. Okay.
Yeah. Yes.
Did you guys look at like maybe like a fine-tuned clip model and see how different, like what different roles that attention head could maybe take on if like the model's actually fine-tuned?
Yeah, so that's a great question. I haven't done that. So there's some existing work on trying to understand how fine-tuning affects models. The work that's been done has actually mainly been done for language models. There's only actually like a small number of papers, like maybe just a couple. So I remember there's one that basically looks at how like base and fine-tuned model do this task called entity linking, which is like tracking which entities are like the same or different in a sentence. And their claim is that actually like the fine-tuned model does it basically the same way as the base model, but just like better, like all the components become more robust. But we also, we've been playing around with this also for like in-context learning tasks, like do fine-tuned models, like do like RLHF models, do in-context learning different from like base models. And we actually, like, anecdotally, we found some differences. So I think the jury is still out. I think it's actually like a very actively explored area. And as far as I know, no one's done this for images. So like maybe you could be the first one to do it. Yeah, so understanding, I think there's a lot of different forms of understanding. To me, I feel like the best test of understanding, or like one thing that like real understanding should lead to is like control, as in like, if I really understand a system, I should be able to understand how to like intervene on it to get the changes I want, right? Like in biology, once we kind of understood that DNA was the code of life and we like understood how DNA encoded things, then you can start doing cool things like, you like inject DNA in a cell and get it to like synthesize new proteins. And like, this is actually like the basis of a lot of like pharmaceutical drugs, right? So I kind of feel like right now we're only just starting to do that with neural nets. And I think that's how we should be trying to ground a lot of our kind of scientific investigation. So, the example I gave where, okay, we can like remove this like location cue to show that like, we really did find the location head. We didn't just like tell a nice story about it. I think that would be a basic form of that, but I think, we should be doing that like much more deeply and systematically to kind of like prove that what we claim we understand, we actually understand. Yeah, so that's an interesting question. So there is work on this, or like there's basically this idea called constitutional AI, which is essentially trying to do this. You like have a model output something, and then you have it like critique its own output to try to improve it, and then you fine tune it on like its own kind of like improved output. And the claim is that this like does kind of improve model behavior. It's a little weird though, right? Because you're like creating this feedback loop where the feedback loop itself is like the same as the thing that is getting the feedback. Like it feels almost like some like Gödel like incompleteness thing that like it shouldn't work. But yeah, so empirically it works. I am kind of a little wary of whether it actually like asymptotically works as you keep doing it and models keep getting better. But you could also, you could imagine a bit more of a complex version of this where a model does interpretability research on itself to understand its own representations and reasons about the ways in which those representations have problems and then fixes them based on that understanding. So that's actually kind of a dream of mine. Like I feel like I feel like this would be like really awesome if you could do this. And that feels a little bit less like it runs into these like paradoxical problems because instead of you're using a system to fix parts of the system rather than using a system to fix like the same entire system. So intuitively, it feels more robust to me. No one's actually tried to do that, but I think that would be really cool to try.
Do you think that the current algorithm could be used to identify modes like that, or like would you what are some maybe like improvements or adaptations?
I think you might have to do like a bit of modification to it, but I think like the basic ideas that I kind of described here, I think it's not I think it would not be very hard to get those cases. My sense is actually that the Gemini stuff was more of like a management and testing failure rather than a technical failure. Like I think basically like the process for releasing that model was like a very bad process, like just from an organizational perspective, and that there were like people in Google who like very much had the capability to notice those problems, and maybe some of them even did, but just like didn't really have the like right incentives to voice their concerns or the right place to do the voicing, or just didn't have the right access to the model to like find the problems in the first place. But yeah, I guess my answer is yes. I think you could definitely find these problems automatically. And I'm not sure that was the problem that Google had so much as like a kind of like failure of management is just kind of what I've heard from just like generally talking to people in that space.
I just want to get your thoughts on what like generally you think is opportunities regarding generating hypotheses. Like for example, if you're taking a look at reasoning, could you, with a reasoning data set, ask the model to do you think there would be value in asking the model to like critique its, or like generate hypotheses on why a model exhibited failures in reasoning?
Mm-hmm.
So yeah, just generally like the generating hypotheses kind of applied to different domains.
In general, like it's a very powerful use case for LLMs. Why? Well, right, they have this large context window, so it lets them see more data at once than we could see. So then this, like, I guess any hypothesis that like requires kind of looking at a lot of stuff, I think these models are going to kind of have an advantage at. If it requires like very detailed reasoning about like a single example, then I think that's also something that like they could become good at, but it's like less out of the box there, because maybe now you need to think about, okay, how can I like decompose that problem into smaller pieces that are kind of like easier to like think about and notice problems in. But yeah, I think that's one thing is the context window. The other thing is just models are pretty good at just being kind of creative and coming up with stuff. Like actually, when I'm trying to think of good examples for like my lectures or for like essays I'm writing, I often just tell GPT-4, I want a good example that kind of has these properties, like could you come up with something for me? And sometimes it's not any good, but like sometimes it gives me things that like I wouldn't have thought about that were like pretty valuable. So kind of just like creative generation is ironically actually something that LLMs are pretty good at. I think the main thing is like how to ground them, right? Like they're good at creatively generating things, but they kind of go off the rails. So I think that's why this is like a really killer use case, because you have this data that is kind of grounding the generation and like keeping it on track.
I think the speed of human understanding language models will be faster or slower than model development by themselves, because we're talking about using AI to understand AI here, and you would probably want a stronger model to understand the model, and then you want the model to be stronger so that you can use it to understand the stronger model. And it's kind of like a loop here.
I mean, my hope is, I guess I have two hopes, right? So one is actually that we can actually use weaker models to understand stronger models. Okay, why might that be possible? Okay, so hope one for why it might be possible is that you can give the weaker model, since it's like kind of has control over how it interacts with the stronger model, has some advantages, right? So for instance, if, let's say you're a lawyer interrogating a witness, you could like ask them a bunch of questions and try to catch them in contradictions, right? To get a sense of whether they're telling a consistent story or not. If you're a weaker model trying to, understand a stronger model, you can do the same thing. And in fact, you can do even better things because you can like ask it some questions and then you can like flush its context so it doesn't even remember what answers it gave to those questions, and ask it some more questions. So then you can tell if it kind of has some like coherent underlying model that it's being faithful towards, or it's just like saying random stuff. Right, so that's just like one example, but in general, I think there's these things you can do to give the smaller model an advantage. The other thing is that understanding and acting are two different skills, right? So models, you can have a model that's very good at understanding things relative to how good it is at taking actions or doing things. Or you could have a model that's very good at doing things relative to understanding things. If it's very good at understanding things relative to doing things, then you're like in pretty good shape. And I think a lot of that just comes down to the relative amounts of data in the pre-training data set that kind of correspond to those different tasks. So we can just have a lot of data out in the world that is about understanding model behaviors and have that in the training data, then this is kind of hope two for why smaller models could understand bigger models.
So have you found any differences between the activation vectors that, like when you're talking about labeling, and I'm not sure if it's labeling activation vectors, when you're talking about the basis and the PC that you're doing with strings, have you found any like noticeable differences between the type intentions that are early on in the transformer versus later on?
Yeah, so good question. So in this case, actually, everything I showed you was from late attention layers. So this is because of a kind of strange thing about CLIP, which is that it turns out like only the last 4 attention layers actually like write to the output. Or like all of them could write to the output. But basically, there's like, after all of the layers, there's a thing called the unembedding matrix, which kind of like puts things into the final representation. And empirically, all the layers before the last 4 write in directions that are orthogonal to the unembedding matrix. So what is this saying? What it's saying is they're all kind of doing scratch work that is like setting up the information needed for the last 4 heads to do their work. So in this work, we were kind of only looking at these like final direct effects on the output. So I only know the answer to the last 4. Other than that, the other ones don't have a direct effect on the output. They all kind of only go through indirect effects. We're currently trying to understand the indirect effects. Yossi's been working on this, but it's a lot more complicated, I guess. Or at least we've been having, it's been harder to kind of decipher those. So I don't have an answer for that. I think for LLMs, people have looked into this and they have answers. Where, it's kind of what you would expect. More abstract concepts tend to appear in the later layers. I think, there's basically like 2 routes, right? There's the behavioral route and the like interpretability route. I think for the behavioral route, I'm excited about just like scaling up these explanatory tools, right? So can we make AI systems very good at like automated data analysis and categorization? Like basically this kind of stuff I was talking about, like the second to last thing I talked about with like statistical models that have like natural language features as their features, as ways to kind of like uncover lots of latent structure in an explainable way. Yeah, I'm pretty excited about scaling that up. There's also so that lets you kind of like understand the behaviors once you've seen them. The other question is like, what are the inputs you should actually give to the model? So I think that's more challenging. That's kind of like sort of like model inversion problem. But I think that would be the other direction to scale up. Then, yeah, for interpretability, I don't know. Yeah, I think we should just find all of the concepts in all of the models, like kind of. We did it for the direct effects in CLIP, so I guess next step is indirect effects. I guess also I think we only really found a subset of the directions. I think we found maybe like 50 things in each head, but there's probably, thousands in actuality. So that's another direction to scale things up, and then just taking, other models. I think all of that's pretty exciting. I think it's a good research direction. There's a lot of, it's like in some sense fairly well defined, but I think there's a lot of like very deep kind of technical questions and challenges on how to actually execute it.
Yeah, so do you think there's any way we can address this behavior models given the...
Well, in principle, if you can find them, then you could fine tune on them to try to fix them. Right, so that's the behavioral route. I don't know if that's been demonstrated yet. I know Reichi has been trying to do this. Then another one would be, I think if you understand the internal representations, then you can kind of do surgery on the model to try to fix it, right? Like, I think the example I gave with ablations from spurious cues would be a very crude example. I think that's not really what you want. But I think there's, right there, like for instance, you could imagine that there's just like directions in activation space that like trigger better or worse behaviors, and if you can just like find the right triggers, you can actually like make the model like work a lot better, or kind of like remove bad triggers so that it like can't, be triggered to do bad things. So yeah, I think that would be kind of the other route.